Okay, well, I guess we will get started here, and hopefully others will come in the meantime. So today we're going to be continuing our work through a set of important topics involving processes and technical aspects of modeling. Having spent the last two lectures speaking about state space and some of the intersections with issues in data science, we're going to be turning now to a topic that holds a certain similarity to that, uh, but it also uh, is going to uh, be a bit broader in its import, in its containment. And that concerns the whole topic of observation processes. And the, this is an area of modeling that is often not really talked about. It's often viewed as kind of something that's off to the side of the real purpose of the model, or just sort of an accident, or an auxiliary or ancillary part of the modeling process. I will note, however, that within the context of agent-based models, it often is something that occupies a very large part of model logic and sometimes model mechanism as well. So within models, we commonly are going to have some underlying governing processes that sort of shape model evolution in some particular way. We've talked about ways of encoding rules associated with models, and those rules drive the evolution of the system. And we spent much of the last two lectures speaking about the uh, implications of evolving system state for dimensionality of the system. The fact that we have a lot of coupling leads to sort of lower dimensional behavior, et cetera. We're going to be talking today about this broader prospect of observation processes as they relate to model behavior. And I am just going to share my screen. Unfortunately, it's taking an especially long time these days. I think it may have some interaction between Linux and Zoom here. But I did also post a model, which may be of interest. It's called ABM Model for Birth Death, if anyone would like to go see it. It should be posted in both learning management systems right now. And we'll probably open it up at some point to run it to illustrate one or more points here. So I had mentioned that agent-based models evolve over time, and it makes sense, it bears emphasis that such models routinely include a need to output results of these runs. These results take many forms, many types of outcomes and output measures. But what collects those is also important. And we talk here of observer processes or observation processes. And what's notable is that these processes, while they depend on model state, while model state may have interacting processes within the model that drive its state forward, that drive the current situation, the model forward. Observation processes, in the strict sense I'm going to use them, are epiphenomenal. They're dependent upon the state of the model, but they don't drive the state of the model. They observe the state of the model. It's as if they're a step removed, a step above perhaps the rest of the model, and they're observing what's going on and reporting on it, but not directly shaping it. I'm excluding here, and you could argue that, there's some observation processes within the model. We saw them in the discussion of hierarchical models, where, for example, cities undertook interventions based on prevalence levels within their own cities. That would be an example of an observation process, them collecting information periodically on how many people are ill within their city and using it to make a decision, which would be part of model proper. I'm speaking here about the bulk of observation processes, often the large majority, which do not shape underlying model evolution, which are downstream, you could say, of the rest of model evolution. Data from the model state over time flows down to be computed in these observation processes. And there may be a data analysis phase that is computing, undertaking analysis of the results of these observation processes, tallying things up, boiling the information down into forms that are easy to understand, visualizing it, etc. In some cases, and in many cases, in traditional models, in almost all cases, these quantities are part of the model, or these processes are part of the model. We specify the model evolution, the rules for model evolution, the kind of core logic, the governing processes of the model. And we describe the observation processes at the same time, and often using overlapping mechanisms, like similar building blocks. We build it up. In many such models, we have data analyses, which further go on. And so we may have visualizations of the results of these observation processes. We may have summaries that we output. So maybe we'll turn to that model, the ABM model with birth-death, the rather bluntly named model, and we're going to run it. And one thing we'll see here is a visualization of some underlying system. We have people, we have them either susceptible or individuals can be pregnant or non-pregnant. If they are pregnant after a certain period of time, they will give birth, and by performing birth, a baby is added to the model, and the baby is linked up to its mother, and individuals are correspondingly linked in networks and are placed in positions that dictate the connectivity. So they're connected with, two people are connected if and only if they lie within a certain distance of each other. And you'll notice here that we have some reports here of cumulatively infected people. I'm not sure why this is saying cumulatively. It's clearly the number that are either infected right now or more likely. More likely, these are the number of new people that are infected. We could easily check this out. I apologize for the mislabeling there. But we can also see the visualization and codes through color of various sorts, the color of the nodes themselves, their infection status, the node boundaries indicate whether or not an individual is pregnant. And then there's color of connections between nodes that indicate whether a bond is between a child and mother, or whether it's between another, it's a different type of relationship. Okay. Now this plot here, if we go to main here, and we were to go over to the plot, what we would find is that it's using a certain data set. This is a rather older style of model, I'll note. This data set calls off to a reporting function of sorts, or a function that gathers some statistics within the population. And if we go look at the population, it defines the statistics. It counts the number of individuals actually currently in this infected state. So it's a prevalence count. And it's a prevalent case count at any one time. So here we have observation processes. We have this plot, which is periodically updating every one day. It updates starting at time 0. And we have this visualization, which is characterizing using multiple types of visual metaphors or visual mechanisms, the status of people in the model. What we see here is a reflection, in short, of observation processes in the context of said model. Okay, I'm going to stop this and return to my slides here. So those processes, the plot that showed things, the visualization, are epiphenomenal. They don't influence the evolution of the model. In this model, and more broadly, visualization serves as a key source of insight. What's going on inside ABMs is often challenging to understand well, and to summarize effectively requires quite a lot of thought. Visualization is not eye candy. It helps us give insight as to whether a model is behaving appropriately, but more deeply, it can clue us into unexpected emergent behavior. It can identify important aspects of model dynamics that we might not otherwise have noted. And, I'll just note that in varied simulations, visualization has clued us into many important insights. I'm reminded of a case where we're working with a model of chronic wasting disease, a fatal, lethal condition involving deer, or cervids more generally, deer, elk, moose. And we were, it's a prion-based disease, so these misfolded proteins drive it. And we had been working with an aggregate model, which characterized levels of prevalence. And, I had always long felt that an aggregate model might miss really important drivers for transmission. And it turned out that hunch was sound. That hunch was accurate. Upon building an agent-based model and using even the most basic of visualizations from it, what we found was an issue that was obscured by aggregate modeling, namely the spatial concentration of prions, was really immediately highlighted by agent-based modeling. The fact that prions tend to concentrate in certain regions visited by deer who excrete them in various processes, or with a deer carcass that decays and spreads prions in the area. There can be very high buildup for prions in certain highly trafficked areas. This is important because these prions can live for a decade or more in the environment and infect animals subsequently who may browse in that area, eating grass, etc. So the fact that we had non-uniform concentration of prions, the prions were trafficked, were built up extraordinarily heavily in those areas that deer visited, was extremely important. They were being dropped by deer because they're visited frequently, and they're being picked up by deer because they were visited frequently. Now, that's not to say that certain aggregate measures weren't important. Oh, they certainly were. But we could understand those aggregate measures in terms of the number of deer who were at various stages of infection much more effectively following a visualization. Spatial dynamics are often we need visualization to be able to understand them effectively. There are other tools, like in topological data analysis, that can bring out, can help us recognize these, but the human visual cortex is extremely effective in allowing us to understand these factors. We often use more classic mechanisms for summaries as well, whether they're visualizations of variables over time or summaries and things such as pie charts. We can visualize states, within spatial environments, capture aspects of context visually in ways that clue us into very quickly to what's going on and really play to the strength of our visual cortex. We've seen these things in passing in many of our models, this model of crowding, for example. This is a model of clinical progression of patients receiving treatment for end-stage renal disease, as I recall, and sort of summaries of their status over time, both with numerics and with color coding that indicate aspects of their current status, and here for physicians attending to them. And as I recall, some aspects of the load of these physicians in terms of dealing with challenging patient dynamics. Scatter plots end up playing a very large role, in my view, in bringing insights into the emergence of patterns within agent-based models, with a scatter plot characterizing, say, with each dot representing a particular agent and one axis representing one characteristic or aspects of state of that agent, and another characteristic being highlighted by the y-axis. We can often understand high-level emergent patterns. I alluded to this, of course, in the discussion of state space, when I noted that coupling in these models, as well as the structure of the rules of the models, dimensional considerations, conservation, other properties, can lead to structured patterns involving these things. And we often see associations here that are induced by the emergent patterns of the model, from models that involve agents circulating over landscapes, potentially inducing results that exhibit important associations. This is a model of trucker behavior by my student Eric Redekop, involving trucker health and truckers moving around the interstate system within the US and visiting rest areas shown in red, I believe, which have various levels of food that they afford to truckers, and trucker health is affected by the quality of the service offerings within those contexts. This is another example of scatter plots showing individuals who are affected by who are reached by the Addictions Recovery Community Health a program, or otherwise not, for percent of ED visits and total time in homelessness here. Okay, I'm not going to dwell on this exhaustively, but I hope I'm giving some flavor of types of visualization observer processes. With agent-based models, we have a need for, we have a direct benefits being offered by observation processes, and we have a need to manage them within our models because often they occupy a large fraction of model logic. I will note that from a methodological standpoint, we've recently, this is within the past year or so, worked towards addressing the needs of observation processes in aggregate in models. Observation processes are sort of the poor cousin of many models. They're kind of viewed as an afterthought, with the main attention being the main point of focus being the model logic itself, and observation processes get treated as they play second fiddle. They get treated as like the neglected stepchild of this process. The things that are just kind of pedestrian outputs, but they actually end up having a set of very big needs, not least of which is to avoid obscuring this model logic proper, the sort of governing processes. There's also a need to make these flexible to enable, flexible to disable, to separate them from the model logic, to use different languages, such as domain-specific languages for these, to be able to turn them on and off according to stakeholder, to be able to defer some of this computation, if you think about it. If we have data, if they're downstream of the model, technically speaking, they don't have to be computed during the model operation itself. Like, we could save away this data coming down here, and we could, in fact, compute these observation processes later as needed, as desired by those examining model, interest in model dynamics, instead of running it during the model operation. The model that I showed earlier, that ABM model with birth death, it was helpful to be able to see these visualizations, but it did slow down the model. Observation processes can sometimes exert strong and computational load on model evolution. And in many production quality models, there's a desire to defer or potentially make optional certain of these observation processes to avoid slowing down. So the model itself can run more quickly, and then we can reflect on that run later. So I've emphasized many of these. I will note that observation processes are among the components of the model most different in where stakeholders, people who are not directly the modelers, who are part of the modeling team, who are typically from interdisciplinary, from background across many disciplines. It's not unusual that you might have 5-6 different disciplines represented in the modeling team. Different areas of health science, including health informatics, potentially those from background more on the epidemiology side, the clinical side, with different specialties, administrative side, etc. Often different members of the team will have different interests when it comes to observation processes. And so what you show to a different stakeholder will often be rather different. So often you want to have user-specific enablement of these. To support an reflection on model outputs, there's often a desire to output aspects of model state over time. And often we speak about trajectories and having trajectory files by which we save information away. These slides, which I'll be posting to the LMSs hopefully later today, have lots of information about how to build these things in AnyLogic. I will note that that's a platform that makes it comparatively easier, I should say, than many other frameworks to store away some information, but where truly custom information can require considerable coding to store things away. There's a lot of basics like data sets can be exported easily into spreadsheets. There's an ability to take data output in a plot and copy it as an image or as data into a spreadsheet, etc. But when it really gets to custom constructs, you will often want to or need to use custom code. An important matter within this area is recording of results. Many outcomes are periodically reported. Some are reported when events happen, some significant event, an outbreak is declared or what have you. And often there's quite a number that are cumulative or summative over the time frame of a simulation and that are output at the end of the simulation time horizon. So there's a balance here when it comes to what you output more data, and in general having more observation processes can support added insight, can support learning, can supporting understanding model behavior, and in some cases providing that information can mean you don't have to run the model again. On the other hand, it also imposes load. It leads to greater amounts of logic and cruft being combined with the model. And it can obscure attention on the underlying model dynamics by focusing a lot of attention on the observation processes. More than that, often what you find is that these processes here, these observation processes, these downstream ones, they evolve over time. What stakeholders are interested in may evolve over time. And there's often a great deal of logic that's put in a model at one point or another, but gets outdated or gets of less central interest, gets stranded. And it still occupies a lot of space or a lot of mechanisms within the model, which, again, make more complicated model evolution because there's a lot of extra bits of code around that need to be updated if the model changes a lot, or that obscure the clarity with which we can observe these underlying model governing processes. So often these observation processes constitute a very large fraction of model logic and a growing fraction as time goes on, because more and more observation needs come up. Old ones become less important, but the code is still there. It becomes hard to remove this code, hard to evolve it as the model evolves without removing large chunks. And it generally slows the model down while it runs, but also the nimbleness of model evolution. So I somehow skipped forward here. Some best practices are separating exploratory runs from production runs. So, having production runs without visualization and exploratory runs that use visualization, and producing most figures post-processing. So rather than trying to create images during the model run for things, considering producing those after the fact in tools of your choice, whether it's R or Stata or Python or what have you, which often have more sophisticated plotting libraries and more options for really fine-tuning graphs, etc. Now, when we output data from a model, when we record it, I will note that there's a keen need to output model metadata along with that, enough to interpret the results. So aspects of model version that gave rise to it, model parameter values, and any scenario name, and potentially aspects of who ran it, when it was run, etc. So bear in mind that like managing the outputs from ABMs, if you're outputting files, there's a discipline that has to take place to manage that data effectively, to keep it meaningful. If you lose track of what assumptions were behind outputs, if you lose track what model version was used to produce certain results, if you lose track what scenario was involved in producing results or parameter values, you will often find those previously output results close to meaningless or are actually meaningless because you won't be able to interpret them. So there's a key need to accompany model output by metadata associated with that. Common outputs from models, when we think about model output, what do we output? What information do we output? If it's not the state of all agents, which we only occasionally do, we will do that in some cases, but it is very computationally intensive. It can't be continuous, so it has to be, only discrete, and it comes with fearsome overhead for what's called IO for the cost of writing it out to files, etc. It's extremely voluminous, and I would only undertake it under very certain circumstances, very select circumstances. What information do we output? Well, often you're interested in assessing, evaluating the success or benefits of certain scenarios, say, when compared with baseline. And so often you have certain outcome measures that you have in mind by which you would judge a scenario, whether it's improved the situation or not. Those are obviously key things to think about outputting. If you have elements of model that have comparators in the world, from the model that have comparators in the world to which you want to you want to compare with model results to assess the reliability or assess the fidelity of the model to those empirical outputs, or to understand how the model has changed things relative to empirical data, or the degree to which it explains empirical data. Often you will be selecting things here for your observation processes that summarize what's in the model in a way that allows it to be compared with what's seen empirically. If there are certain outcomes you're interested in that have certain possible drivers, often you will have the model output information that may clue you in as to which drivers are driving, which mechanisms are driving model output. Maybe you have agents who can be affected by surfaces or other people, and you want to report some sort of information on how people are getting infected, or perhaps where they're getting infected, in what venue they are getting infected, at home, at workplace, in the community, etc. I believe there's a previous model I've shared with you that involves that, tagging that information and being able to report it. And visualizations of some aspects of high-level model behavior that might clue you in as to whether the model, sort of the essential dynamics of the model you're interested in seeing, to build some confidence the model's operating correctly, and to give some sense about what's going on and if there's interesting behavior observed. Now, it's notable that when we are reporting model quantities or model collecting data from model outputs, that we will generally need to report not only snapshots of the model state, some sort of aggregation. For this model we were running before, it was the number of people infected at a given time. You may recall with Maine here, we went and we saw that at any one time, we could call off to the infection status and report the number of people who are currently infected. That's an aspect of what I would call cross-sectional longitudinal data, cross-sectional data. It reports at a given time, a snapshot, how many people are infected now. A separate need, also well represented in some of the example models, I believe, that I've shared with you. Certainly, I will double check and provide another model if that's not the case that shows this, is changes in model state. So this would be things like incidence. How many people have been newly infected within the past week, for example? How many children have been born within the past month? How many individuals have died within the past year? These are all aspects of what I might call flow statistics. I mean, they relate to changes in model state over time. They're not reducible to any one point in time, right? The number of people who have died over it does make sense to report a number of people who have died at an instant, over an instant, because it'll be zero over that instant. Instead, we have to consider it over some period of time. And it's a common need within models to have some mechanism for computing that, for computing these quantities periodically that represent changes over some period of time. And I give two ways to accumulate these. Again, in the model library that I've provided, there's a number, I'd say at least 10 to 20 models that demonstrate this, probably over 20. Commonly we'll have a variable that accumulates it over time. Every time something happens, we add to that variable. And if we wish to tally it up over on a per month basis, we zero out the variable at the beginning of time, and then we tally up each time we output at the end of that time period and zero it out again. Or we accumulate some cumulative number and we subtract off the number as it was a month ago from the number now to get the difference, for example, in addition to accumulating the total. Okay. I could go into some specifics with any logic here. We'll do that tomorrow during the lab. We'll show some aspects of model outputs, including this kind of accumulating flow statistics, accumulating summaries of changes in the model, and exporting to files. I will just say that there's a important possible use of databases here, and I'm talking here, for example, relational databases that you can query with SQL, with SQL, structured query language, which many of you will know, or outputting to large textual databases that you can query using mechanisms in using R packages like dplyr, tidyverse, etc., or with tools in the Python ecosystem. Right. Okay. So maybe what I'll note here, and again, I provide some guidance here for those seeking to, in any logic, easily output mechanisms from plots, from variables, from data sets, etc. Lots of specifics on this that some people may be interested in. We'll be exploring some of these things tomorrow. I will say the having exporting to the so-called console to sort of textual output is also valuable in many cases. We can report messages that characterize dynamics of the model, can report when some significant event happens, can log when certain things happen. And that can be very helpful for debugging. It can be very helpful for knowing, indeed, if certain information or certain actions are taking place, certain processes are, in fact, operating properly within the model. And in some cases, it can provide us information to use in our analysis. Generally speaking, because it's limited length, it may be mixed with other output. It's less structured. If we want to use some of this data, we will instead output it to a file as well. And this can allow for persisting the data. I give some comments on exporting to databases here. We've certainly made use of that in quite a bit of our work. It makes data management easier in some ways. It can support very large-scale data. It can support flexible querying, including from many frameworks. It can support easier cleanup when you, for example, discover a problem with a version of the model and you wish to get rid of all the data sets associated with that. With proper indexing, it can be quite performant. It can be easier than dealing with very large numbers of files stored in folders. It allows decoupling in some cases of the data the machine on which the model's running, or that is at which the user wishes to analyze is running. I'm not going to comment in detail on that here, except to note that if people are interested, I'm glad to discuss this. We've had a number of lines of modeling where this has been done extensively, including keeping, and this is an important need, keeping track in the database of the model version used to create it, the parameter assumptions, some description of the goal of the run, who ran it when, these sort of metadata, having that part of the database, and a database schema that's suitable for your modeling project for the information you wish to record. And you can save information away here. Okay. I do want to finish up with a discussion of visualization. I had alluded to this earlier, but I want to hit on it a little bit more. Our visual cortex, the human visual cortex, is extraordinarily good at recognizing complex visual patterns. And complex emergent patterns often stand up to us visually, much more so than if we see columns of numbers or reports that are just numerically summarized. We can often much quicker see things when it's visual. Much quicker see patterns, see subtle differences, clue us into aspects of model emergence. Often a picture can be worth 1,000 words. Visualization can capture subtleties in model runs that clue you into something going on. It's not that the visualization has to summarize all of model state. We talked in the past 2 lectures about how in ABMs, just as in real-world systems, there's coupling between variables. So if there's something abnormal going on or something really interesting from the standpoint of emergence in one variable of the system, you may not be outputting that variable, but you may be outputting other things affected by that variable, right? And those things, when you display them visually, may clue you in to something interesting about the dynamics that allows you to drill down and figure out what's going on in those factors driving it. So often, it doesn't require extensive, exhaustive, comprehensive visualization to get real benefits from it. Visualization of just a few things done well, taking advantage of visual richness that is possible, can really give you important insights about model behavior when it shifts, changes in model phases or regime changes in the model that can clue you in to really important dynamics. So a good visualization here can clue us into interesting dynamics. It can allow us to spot problems in the model, bugs in the model, things that aren't working more quickly. It can allow us to debug the model more quickly when there is a problem. And in some cases, in many cases, it can help communication with stakeholders. Stakeholders are drawn to visual constructs in many cases. There's effective storytelling around visualization that's very powerful. And I would urge you to think about taking advantage of it. It's one of these great benefits of using an agent-based model that we can play to its strengths with visualizations. I noted the choice between doing live simulations with high computational cost versus post-production, like after the model runs, saving away some aspects of model state, snapshots, changes over time for different intervals of time, and then doing visualization post hoc. It requires exporting requisite data, but it's very powerful. And we've gone so far in my group to use mechanisms, certainly many more traditional mechanisms of histograms, scatter plots, heat plots, density plots, violin plots, etc. But also importantly, 3D visualization tools, where you can rotate, within a Shiny app or what have you, in R, or you could have using Oculus, now MetaQuest, 3D visualization to understand model dynamics. Okay. So some ideas for visualization. Model summaries. Often an HMS model like that we've seen many times in this class, certainly for this model, there's a lot more going on here than can be characterized exhaustively by a stock and flow model. But a stock and flow model can summarize, not completely, but that's not the point. It can serve as an effective summary of what's going on. You could have a stock and flow model as a visual metaphor that shows how many people are in susceptible state, how many are in the affected state, how many per week are transitioning between them, the flow between them. It's a mode of summarizing what's going on at a detailed level in this model visually. And we've used stock and flow model metaphors for that, with the stock and flow model, to be clear, not running autonomously. No. It's just being driven by the data from the ABM to tell, okay, what's the value right now in this stock, the value in that stock conceptually, and what's the flow between them, value the flow in ways that summarize what's going on in the ABM. Scatter plots. We talked about that. I don't think I need to elaborate on it more, but we've talked about using that to good effect to kind of characterize the associations between certain model outcomes. GIS visualizations, whether it comes here. This from a participatory modeling that Wade spoke about the water model and First Nations community in Yellow Quill First Nation, where we have individuals and homes and pooling and individuals need to get to school or to dialysis appointments or to the clinic, et cetera, and their health can be affected if it's disrupted and waterborne illness. These sort of GIS visualizations can be very effective in summarizing aspects of model state. Network visualizations, we saw some aspect of that earlier. Density plots, 2D histograms, very effective at summarizing aspects of model behavior over many runs. We'll be seeing that soon in some of our discussions of sensitivity analysis and potentially calibration. Box plots and violin plots. Jeff, you've used violin plots to great effect, and there are sort of more sophisticated version of box plots for summarizing model outcomes. When we have variability, state-space plots, we talked about those last time, and it's a very powerful tool for visualizing aspects of model behavior that complements, I don't think I need to expand on this after those two lectures, what we see with time series. It really provides an alternative lens for understanding model behavior that you could argue is equally rich to time plots, but provides different insights, it emphasizes, or it can bring out different insights. Distributions, histograms, cumulative distributions, pie charts, all of these are really valuable. I give some aspects here on scatter plots between um, time since a certain period and some aspect of state, time since someone joined the program and some sort of outcome. I think that's what we kind of have here. This is total time in addiction versus the percentage of EDE visits that they experience, for example. Total time in homelessness versus percent of ED visits. Between parameters and aspects of state or two different aspects of state. And you can use colors of dots to indicate aspects of characteristics of the person being summarized. Here we're summarizing for different age ranges, characteristics of kind of susceptibility of individuals, and summarizing it over time here, different periods of time. This is yearly accumulated incidence rate over time, and I think this is monthly incidence. These are sort of characteristics of the population of that age. So here we're summarizing model state in different subgroups of the population, et cetera, trying to match and using different measures, cumulative and non-cumulative. This is age distribution, incidence by age. This sort of cockpit view provides a lot of information. Here, Wade's model that you had seen before, the health status of the population, conditions being treated, waterborne illness status over time in a stacked chart. And here we have output from the model that characterizes narratives, characterizes stories. Or at individual story of a particular individual can be a powerful thing for communicating with stakeholders. Modeling, as my colleague Jeff McDonald told me probably it was 2011, 2012, maybe it was 2013. He, urged me to think about modeling as storytelling. Modeling is storytelling when you speak with high-level stakeholders and you're trying to convey the essential insights from a model. Modeling is storytelling when you speak with people with lived experience and trying to elicit their often tacit knowledge to help confirm or challenge and critique the reliability of model outcomes. It's storytelling and building their confidence in the model. It's storytelling when dealing with clinicians and dealing with other health scientists and giving them a flavor of what's coming out of the model and eliciting their lived experience within the system, their professional judgment in whether patterns are coming out. And one of the ways we can elicit this is with narratives coming out of the model, individual narratives that complement our aggregate narratives. Again, playing to a strength of agent-based modeling. Geographic visualizations or spatial visualizations often speak to people's appreciation of the model in a deeper way than purely numeric ones. That's all we have time for today. Hope that gives some understanding of some considerations that come into play when it comes to model outcomes. Agent-based models have incredible richness of possible outcomes compared to aggregate models. This is, on the one hand, can be viewed as a liability. On the other hand, it's a tremendous asset. It's a tremendous asset for building confidence in models, for eliciting lived experience, eliciting understanding, eliciting ideas for interventions. It can also be formidably helpful when we're trying to understand model behavior, when we're trying to assess whether that behavior is reasonable, when we're trying to spot any problems in the implementation of a model, when we are trying to spot problems in the design of the model, when we're trying to understand emergent patterns coming out of a model, or even spot such patterns. Outcomes from model need to be chosen carefully, and they can be formidably effective in cluing ourselves in to important aspects of model dynamics. So thank you very much.